Hello, everyone. You're with us here, and we can make it into the drink session after this. Let me get going. So I'd just like to give a special thanks to the authors who helped put this presentation together and really get those nice, beautiful display vehicles outside in the exhibit area there. So really, it wouldn't have been possible without these guys, so round of applause to them. So at Rivian, really, safety is always top of mind, and I really wanted to show you guys why and how we can do that at Rivian. And so this is kind of like a little map of the R1T and R1S vehicles at Rivian and kind of the awards that we've received with IIHS that kind of show that our commitment to safety and maintaining a safe vehicle. So you can see the history of IIHS Top Safety Pick Plus and Top Safety Pick awards that we've gotten through the years. Kind of digging into that IIHS a little bit more. So this is the IIHS SORB test, so the small offset rigid barrier, where we're impacting the vehicle, 25% of the vehicle into a rigid barrier. And really this one is, you're missing a lot of that main energy absorbing structure, so those mid rails of the vehicle, and you're taking a glancing blow to the vehicle. So it can be quite a challenging impact to deal with. So really how we're managing this is we have what I've highlighted in orange, which would be the offensive structure. And that consists of some of the things like the bumper beam, the cross members, and some of our shotgun structure. And then the defensive structure, so the blue that I've highlighted here, which would be really your backup structure and everything that's gonna take that energy that we can't dissipate in the front of the event by either deflecting that vehicle off the barrier. And then really with that defensive structure, we wanna protect the occupant compartment, make sure there's no intrusion and push in towards the occupant that we might have some occupant injury or stuff like that. Just to kind of dig in a little deeper and zoom in to one of the particular structures that we have. So this is part of our offensive structure, and just taking a really close look at that shotgun. And so you can see, I've kind of highlighted the section of that shotgun there, where we're essentially using that kind of an arm to kind of glide the vehicle off the barrier and really produce some of that really offensive motion away from the barrier to limit the amount of energy that we're putting into the backup structure or defensive structure there. And so how we're doing that is we have this advanced high-strength steel shotgun inner, and that's highlighted in blue there in the picture on the top left. And the value of that is essentially we get the high strength of the advanced high-strength material, but we also get the ductility, so we can create that kind of bend point that hinges that shotgun and allows us to glide off the barrier. Inside of that, we have a reinforcement. So we have this press-hardened steel reinforcement on the inside of that that's really giving us the backup structure that we need inside of that shotgun so that we can push onto the cross members and everything behind it to really start to push and glide off of the barrier. And then finally, we have that hinge pillar structure, also press-hardened steel. And really, its job is to be the backup structure and limit the amount of intrusion we get into the passenger compartment. So one of the big things we've done is we've kind of evolved the body structure at Rivian, and one of the really big ones that I wanted to highlight here today was going from an aluminum to a steel floor structure. And so as I've highlighted here, the Gen 1 product, we had an aluminum sheet floor with an aluminum extrusion for the seat cross member. That's now in the Gen 2 product gone to a high-strength steel floor with a multi-piece steel cross member. And I've kind of highlighted on the left there, essentially you have what that cross member looks like, so the aluminum extrusion in the Gen 1 product, and then going to the Gen 2, you can see that we've kind of made that a multi-piece system. So we have the advanced high-strength steel and then ultra-high-strength steel for the tube in the inside with some structural inserts. And I think at face value, it looks like we've added parts here, things might have gotten a little more complex, but really what drove this was a massive cost decrease, which really was valuable to us and essentially came out to a $15 per kilogram savings. With everything at Rivian, it always comes back to how does it affect the safety and overall safety of the vehicle, and what are the occupants on the inside going to see in a crash event here. So I've kind of highlighted this is the side crash energy management structure, and I'm highlighting the FMVSS 214 50th pole here. And so what you can see in that image is we have those pink seat cross members that go lateral in the vehicle, and then the green battery structure, so those green battery cross members that really give us that lateral stability and support in these side impact events that are pretty severe, to kind of manage that and not allow us to intrude and put that pole in towards the occupant. And so what we're showing in this animation here is a comparison of the Gen 1 product to the Gen 2. And really what I like to highlight is like in that cross member, you can really see that there's, in the Gen 1 product, quite a bit of deformation. You know, we're seeing quite a bit of straining in the part, versus when we look at the Gen 2 product, we've really mitigated that amount of deformation in towards the occupant. The B pillar is not intruding as much. So really, like, as we're saving cost with this Gen 2 change, we're also really, you know, keeping the performance of the safety the same or better. Something else that I wanted to highlight is, you know, one of the big push when we go to the Gen 2 product was how do we save time with essentially building these frames, which in the end really amounts to how much money can we save. Going from the Gen 1 to Gen 2 product, one of the big ones was joining reductions. And really, like, kind of like question is how do you go about this? How do we do these joining reductions? And so really, like, some of the big ones, we're looking at things like variable thickness blanks in the vehicle, consolidating parts that way, looking at things like structural inserts to reduce the amount of different joinings and stuff like that we would need. And then also really going through the attribute requirements for each of the load cases. So whether it's durability, crash, really going through those, like, what do we actually need out of these joints and how much load do they need to take? And so what you can see in that top left table is kind of like a per frame reduction of each joint that we have. So, like, you know, there's really massive numbers there, like 300 plus spot welds reduced from the frame, 8 meters of MIG weld, you know, 5 meters of structural adhesive. So it's significant numbers, and really what that comes down to is a 30% increase in frame output. Similar to what I was kind of showing there with the side crash, I wanted to like dig a little deeper on how did we do this going from Gen 1 to Gen 2 in like something like the frame rail. And so what I wanted to highlight with the Gen 1 is that we have a lot of these reinforcements inside of a uniform thickness rail, and that's an advanced high-strength steel rail. And you can see all that red there represents quite a lot of reinforcement. We also have an aluminum extrusion that's got adhesive and flow drill screws going into it to stabilize that kickdown area. We have a lot of transition going from mid-rail to kickdown due to like the ride height of the vehicle, so there's a lot of moment going in there that we need to stabilize. So then going into the Gen 2 product, we switched to a variable thickness blank, so we could really tailor along the thickness or length of the rail, you know, where do we need to put thickness to eliminate some of those reinforcements and really control it in the mid-rail versus having to add all these reinforcements in. And so you can really see going from that red to blue how much was reduced. And then the other addition was adding in a structural insert into the kickdown area, which was a big win for eliminating some of the joints that we had there, so the adhesive and the flow drill screws, because this insert that we've added in is essentially, you know, expands and bakes out when we put it into the paint bake cycle. And it also fills the entire section, so we get very good section stability. And on the left side there, you can see kind of like the heat map that I'm showing for the variable thickness rails that we were looking at. So you can see anywhere where there's the yellow, orange, red, those would be like the areas where we've added quite a bit of thickness to the part to essentially be able to eliminate those reinforcements. And then other areas where we need, you know, softer, the blues, stuff like that is where we're trying to get crush in the part. So this is then a good look at, you know, we've done all these cost down changes, we've reduced a lot of joints, how does it perform in safety? And so this is a look at the IIHS 40% offset deformable barrier crash mode, impacting the vehicle at, you know, just off the center line. So we're really just engaging one side of the vehicle, one side of the crush structure. So we really need to manage a lot of that energy quite efficiently and well. And so, yes, obviously, like, struck side mid-rail is going to be the main load path for this, but it's really going to also be these cross members that we have. So the bumper, the cross members that are highlighted in yellow, and really try and get some of that unstruck side engagement. But I think the really big thing to highlight here, going from the Gen 2 or Gen 1 to Gen 2 product, is essentially, you know, crush mode is looking very, very similar, and we've also not sacrificed any of the kickdown deformation or kickdown bending. And so ultimately what that means is we're not going to be pushing the kickdown into the occupant compartment and sacrificing on intrusion or stuff like that. So really, like, maintaining the same level of safety performance while driving costs down. So I think that kind of concludes my section here, and I'm going to introduce Dan Black to come up and present on the serviceability side of things. There you are, sir.
Matt. Let's see. All right, thank you, everyone. Yeah, to Matt's a testament. I will be discussing how everything he just discussed will affect collision repair. So it's a topic that we don't commonly cover in this forum, but I want to draw you some exposure as to how we develop a lot of our collision repair processes from start to finish, as well as what things can complicate our repair process while we go through it or the development stages. But first and foremost, like Matt showed earlier, we went from aluminum intensive in the floor and we converted it to steel. A lot of opportunity existed not only for manufacturing in this space, for optimizing our process and flow, but from a repairability perspective, dissimilar metals are very difficult to manage in a collision environment. And if we can reduce that complexity with all these varied fastener styles that secure aluminum to steel and insulate it, we can refine the process to repair and prevent contamination at a higher level. For steel to steel, it's the best way to go. The less dissimilar metal contacting each other put us in a much better position to repair that product where we have a lot of uncontrollable environments in a collision repair facility. So that's really well documented through our R1T here and our R1S in this particular view. Very similar. Everything B-pillar forward is common on these products. It's unique from that point rearward. And in our skateboard, all the materials actually remain relatively the same on the outside, so what you see is common substrate. But what changed is we closed in the frame rails a little bit so that we could accommodate for a larger battery pack. So we wanted to add new tech to the vehicle, increase performance targets, and one of those particular caveats was increasing the dimension in which we could package that battery. As a result, we had to reduce the profile of the frame rail in that particular instance. And then as Matt was talking to earlier with reducing weld counts, we did that, closed them in, and we also changed the material to an extent, which made some things very challenging to develop repair instances for the front frame rail and rear frame rails, which we'll get in here a little bit. Here's some inside, some explanation on the guts that Matt also talked to with the nylon structural inserts and things that we did to optimize the product. It just gives you a better view of what exists inside the frame rail. These particular images in our collision repair content, it helps the technician be more aware of what's behind the curtain without having to peel it back before they perform a repair process. And in this instance, I just want to highlight that we're focusing on the front and rear frame rail for what I'm going to call a crash course in collision repair development, because I do not have a ton of time and I could talk about this for an hour, but I'll make it 11 minutes. So let's get through this. All right, so with front and rear frame rail identified here, we had to optimize for repairability in the field. The last thing we want to do is replace the entire frame assembly upon any front or rear impact. This is the most common repair instance in the field is front and rear collision. You'll see that more common throughout any other aspect of the vehicle. And we need to optimize those locations to localize repairs based on where the impact's been instilled. And we do not want to chase that damage from front to rear on the vehicle if it's unnecessary. That would be an entire frame rail assembly replacement and not conducive to the repair process, and it could often relate to a total loss in the vehicle, instantly increasing the insurance premiums. So we want to stay away from that. We want to localize any damage that occurs to the product. So we actively work with our engineering teams as we came in a little bit late to the development process and reverse engineer the front frame rail environment to optimize sectioning. And what you'll see soon in the rear rail is that we have a beautiful joint that's there in the factory that we could work with that already existed. But there was no joint in the front of the vehicle that we had to fabricate and work very closely with our structures engineers to ensure that could come to market. So here are some of the concepts we went through. As you can see to the left is the frame rail concepts for the front. There was 6 different iterations. And believe me when I tell you this, it took over 3 years to develop this for our product, to reverse engineer the front environment, to instill it for repairability. It wasn't initially optimized for this, but we worked closely with all of our beautiful partners internally to provide an excellent result and enable this for the field. The rear zone was a little bit easier since the section already existed. We could sleeve the rear rail from its existing location, use the current joint, weld where it was previously welded. It was more of a 1-to-1 ratio. What was already there, we could reinstill. The front environment did not have any provisions for welding in the front section. Here you'll see in these animations, the left CAE image with the 2 front bumper reinforcements is the base model. The right side's the welded model on the frame rail. They're performing very similar and characteristic, and that's exactly what we're looking for in terms of testing out our systems to ensure we meet that initial production intent. And then in the rear, you'll just see how we're calculating all these strains and loads as they go through the vehicle, so we can begin to get a sense of what we're going to do from a repair perspective as we begin to develop. And that's more critical as we go into testing. So just like any other material on the planet, you're doing a series of coupon testing. We do a lot of tensile testing, lap shears. with resistant spot welds. To the left is a MIG seam weld, and that's a common operation when we section metal and install it on the vehicle. And the weakest point is always that heat affected zone. And we want to ensure that we test it to failure to know what its true performance is for that particular weld application, and it meets the requirements that we initially instilled in the product. So you will see a series of coupons laid across that table. That's just the beginning. There's at least 5 samples of each particular stack-up. Stack-ups will vary based on the requirements of the environment, and then we'll test to failure in each particular situation, and we don't want to have any anomalies in the test, so we test to a larger volume to get an aggregate, so we have a common theme that's been established across the product. And here's some more information on baseline for resistant spot welds, as well as plug welds. These are common operations in a collision repair environment. They have full capability to use squeeze-type resistant spot welding, as you see in manufacturing. The plug welding is somewhat unique to repair, and that's in instances where we do not have tooling access. So if you cannot get the tooling to access both sides of the component to perform those resistant spot welds, it's typically closed out by the time you get to a collision repair environment. And we need to instill a different process, and that requires a series of validation because we're deviating from what was there to begin with, and we need to ensure it performs at that original factory standard. And here's a good example on a drop tower test out in the desert of Adelanto in the Mojave of California. It was a very interesting environment, but we took a rail that was production, and then we performed a repair in yellow. Production is purple. And you can see side by side very similar characteristics. That's exactly what we're looking for. They're fastened to a base plate. The base plate was absolutely critical to ensure the component did not shift. That's why we performed the baseline test first with the OEM component to ensure that that was going to be established as a standard. And then as we tested with the aftermarket or repair component, that we had a comparable data in that particular test mode. And we ran at least, I'd say, at least 12, 13 samples. And here's the rear zone, less complicated as we're using that factory joint. It required about the similar level of impact testing. I think we could pull back on it a little bit from a sample size just because we knew a lot more going into those systems with those substrates, and we were more comfortable with that environment. And here's a simulation for the front zone, once again with that repair stack for the welded application, showing how it's loading, getting all the variables executed through CAE, very critical in our development. That's where we work very closely with Matt's team, and that begins that design iteration cycle. We have a lot of conceptual ideas. We want to put them to the foot. We put it through CAE. We try to calculate what that weld data is. That's where the coupon testing is so critical because we can input that into the CAE to dictate the model more accurately, which really helps us because it should require far less physical testing when you get there, and you'll be much more accurate in your execution. And I really love this slide because I think it's pure beauty. It's a result of a lot of our hard work because it's direct overlay of the CAE model over the physical test. So it shows you that ratio, how accurate is your modeling compared to what physical impacts being exhibited to that environment. If you get 1-to-1, you have tuned your math right on point. You just pat yourself on the back and move forward. It helps expedite the development process the next time around, and it lets you know how mature your data modeling is at the same time. And then one caveat that is really critical, particularly with this product, because it is designed to tow, it's going to handle a lot of tongue weight from the rear. And the rear has a lot of adverse loads, especially when it's bearing additional weight than what's already in the vehicle. It's critical to go through durability testing. And in this case, we have a simulation running in the lower right corner where it's sending a pulse into that assembly where it's been welded to ensure we don't trigger any stress cracking long term, essentially validating reliability on the joint. It's one thing to execute for standards for safety and quality and ease of execution, but ultimately it has to last long term throughout the life cycle of the vehicle as with anything else. And that's what allows us to be confident in our decision making at that point in time. And as we move forward, we did something a little bit unique. We went through a prototype fabrication process. We didn't have a supplier on board to make this for us initially, so we decided to make it in-house. We used our own workshop, developed fixturing and jigs to set it in position, make all the nominal points so we get accuracy, and we built out about 30 assemblies. So we have those in our back pocket. They're in our inventory today for our front frame rail assemblies. It's not something that can be executed in production. And then we optimize it so that we're just using limited components from the original design as opposed to larger skateboards and removing apart from one known good component that would be a lot of sustainability waste. So we've optimized how to manufacture that internally and we're currently working with a supplier to scale that out in a larger volume. And the rear rail was much more simplified because the parts already existed because it was a factory seam. So we were able to use what existed in that instance. In this case, we're going through a lot of validation in our R&D facility where we're using one-to-one skill sets of a technician and allowing technicians to execute with this process with common tools that are utilized in a collision repair environment to ensure it can be fully executed. There's no caveats. We have a fully validated process. We know in a shop environment it can be executed on a daily basis with the proper training and be repeated with consistency. Very critical. So all those variables were executed to the highest standard, well documented, as you'll see here in a little bit. So we have a service part finalization process, install your GD&T data, all the PPAP approvals, you name it, all those proper processes to ensure that we have every metric on the planet to measure our quality, standards, and we can hold ourselves accountable to ensure that there's no defects going into our assemblies. And in this case, this is our workshop, and we did the initial validations by executing to a high standard with fixturing on frame bench equipment that's commonly available to the collision repair world. We validate every piece of equipment we specify for our network, and we want to ensure that this can be executed on their equipment. That's the first most important for them. And then here's another snapshot of our R&D facility, but this is for the rear rail assembly. The previous one was the front rail assembly. Up on the upper left is actually our repair documentation. So this is something that our network has full availability to and is resourcing and referencing on a daily basis to ensure they're executing to the correct standards that we've called out, whether it be weld wire, spacing of welds, locations, and all the other nuances associated with the repair process. And if there's one thing that's known, the vehicle is only going to get more complicated over time. We're going to be putting more technology into the vehicle. There's going to be more complex substrates. But it's our responsibility to ensure that those substrates can then be repaired in a way that's economical for the industry to keep the vehicle on the road. We want to be sustainable as a business, increase the life cycle of products through a collision instance, and this is what it really circles around from a development perspective as well. It's great to develop for manufacturing and enabling repair on the line, but when it gets into a consumer's hands, if we do not keep the vehicle on the road, well, they're not going to purchase any of our products at the end of the day, so we need to keep it in motion. And that's all I have for you. So thank you for your time and your patience.
We're now pleased to welcome Venu Krishnardula to the stage, who will be joining the team for some Q&A. As a reminder, please continue to submit your questions through the GDIS app by navigating to the agenda and selecting this session. All right, so we have a question here. Are you evaluating replacement of the aluminum extrusion rocker with a steel alternative? Was this considered when going from Gen 1 to Gen 2?
At this time, we're pretty happy with the aluminum extrusion right now. It's doing the job that we need. Who knows what happens in the future?
Yeah, I guess we're always looking into new materials and alternatives, so we didn't want to finish up everything for this session, so probably we'll come up in 2026 and see if we can do that.
All right, from a repair standpoint, what strategy is used to repair the areas in the frames that use the nylon inserts?
So in the case of the nylon inserts, our repair zones aren't in that area, so that area is not repairable from a collision repair perspective. Our zones for repair are forward and rearward of those locations. So it would be a full replacement if that area was damaged.
Thank you. Is there any specific training required by the technicians to work on a Rivian body structure that's unique?
Yes, absolutely. We have a litany of criteria required by technicians, and more importantly, the proper equipment and resources used on it. We have internal training, and then we're working on ramping up various welding training for the industry as well to ensure that they're of qualification to work on our vehicles.
Great. Are there areas other than the front of the car that have an offensive body structure?
Typically, no. Like right now, like in our vehicle, really like that front structure for the Sorb crash is like the offensive. I would call most of the other modes become more very like defensive focused.
Let's see here if there's a few more questions. So just from a Gen 1 to Gen 2 design standpoint, how much of an increase in PHS materials was there?
think the PHs mostly remain similar. I don't think there's a huge lot of change, but I think we changed others to IIHS, some aluminum extractions and other stuff.
Let's see here. So going through this